Everyone. This is Tuba. Today I'm going to present background activation blackout for efficient object detection. You can find the useful links. I add all the links in here related to this paper. So let's move. I'm stuck. So, what I'm going to talk today is the motivation of the paper, and I'm going to show the related work, and I will talk about what is the differences, the proposed approach, and the experiments and result, and I will conclude my presentation. So, the training and running a deep learning model requires a large amount of computational power. So it limits the scalability and accessibility of deep learning, especially for resource-constrained environments. To improve the performance in deep neural networks, proposed solution can be split hardware and software aspects. Hardware designed for dealing with zero values, handling sparsity and high precision outliers, on-chip convolutional neural network models, and specialized accelerators. In the perspective of software acceleration, it includes lightweight network design, network pruning, and network quantization. This paper's approach is motivated by previous works exploiting the sparsity of weights and activation. So you can, in this figure, you can see how the proposed approach works. You have your input image and a feature map generated by a modern object detection model, and proposed model's feature map. In here, as you can see, while object boundaries are rough and some foreground pixels are lost, as you can see, there's a hole here, but still it covers most foreground region. So in C, you can see it's still, detect all objects without background activation. So when we check the related work, we can see that traditional object detection methods and overfits are based on sliding window algorithm to reduce computational cost spent on searching on the entire region. With this sliding window manner, the two-stage RCNN series have been proposed, and it successfully actually reduces the number of candidates for background region. However, it still requires lots of computing resources to generate proposal. And on the other hand, like one-stage detectors such as single-shot, multi-box detector, and you only look once, the feature of the convolution backbone network are fed into subnetworks for object classification and bounded box regression. And it still requires to compute all of anchor candidates. So when you check the other network like semantic segmentation and two or multi-branch system like fast semantic segmentation network and ICNet for real-time semantic segmentation, and pyramid scene parsing network and salinity detection, those are not suitable to getting rid of the computational computational sources also. So reducing the computational cost of neural networks can be tackled in various ways, like straightforward approach is to design efficient network manually or automatically, or like quantization methods. But computational costs rapidly decrease when low bit precision data types are used for weights and activation for quantization methods, and there are other dilemmas for all of this work. So what this background activation blackout approach and model promises, like, it consists of two models actually, and one is object detection network and the other is objectness mask generation network. And we in the study single shot multi-box detector used in OD network part as a baseline framework. And this SSD consists of two main submodules, feature extraction network and anchor head network. And objectness mask generation task can be thought of as simplified version of semantic segmentation. The network takes an input image and generates a binary mask where background pixels have the value of 0 and foreground pixel have the value of 1. And this is adapted from like fast SCNN. And this objectness mask generation network, because it has a fast and lightweight semantic segmentation method, so they use this, they adapted from this method. So in here you can see proposed approach. We have an object mask generation before object detection in front of the object based on OD network, and input image and all input features, the convolution layer of the OD network are masked with a binary mask, binary object mask, which zero out pixel values in the background. And you can see element-wise multiplication with this X symbol and max pooling in this shape. This mask operation is implemented as a element-wise multiplication layer, and when the shape of a feature map changes due to the operations such as pooling or strided convolution, max pooling is applied to mask. So its shape always matches that of corresponding feature map. So the authors incorporates OMG and OD networks into an end-to-end model to reduce the computational costs and improve the accuracy by directly optimizing two networks for the final goals. And surrogate gradient method used a proxy derivative function for the backward pass that approximate the direction of the original activation function gradient. The experiment parts will include terminologies and data set and implementation and preliminary experiment. So the number of multiple accumulation operation for a single convolution layer is calculated by this. As you know, a convolution layer consists of triplets like input and output activation tensor and a set of convolution kernel, and also the approximated multiple accumulates, number of multiple accumulates was calculated by this formula here. MS COCO, the data sets used in here is two benchmark data set. One is MS COCO Dieder Pascal log, and MS COCO contains in training part and 115K images, and for validation they use 5K images, and for test part VMK and evaluation metrics they use average precision, while they were using mean average precision for Pascal log. And for fair comparison, all experiments are implemented based on publicly software like MM detection and fast SCNN using PyTorch, and they did a pipeline or medium models to train for some epochs with different GPU. I'm not gonna go details this information, you can find it in the paper. So in this experiment, objectness mask can be generated in many ways. So we can build a pipeline system and run a series of experiments using various mask generation methods, including random mask generation, spectral residual salinity detection method, and proposed OMG methods. So they also use GT instance and bounding box mask to investigate the upper bound accuracy of the proposed approach. You can see the details next slides. Yeah, objective mask generation part. The experiment, let's talk about the experiment. To make an OMG model better recognize foreground region, they used the following three techniques. One is mask deletion, and the other is online hard negative example mining and loss weighting. So for the first one, it expands the boundary of GT objectness mask using a deletion marker algorithm. When an OMG model trained with delayed and deleted GT mask, it detects small and thin foreground areas better. And upcoming figure, you can see an online hard negative example mining is a sample method that selectively uses negative examples having the highest losses because only a small fraction of the entire region is foreground in many images. The baseline model tends to predict background rather than foreground. So this model technique actually mitigates this problem by using negative examples proportional to the number of positive examples. So loss reweighting is a cost-sensitive learning method. So let's check the figure. Here you're seeing MD remarkably improves instance recall of predicted objective mask at the cost of foreground ratio, FG ratio. The effect of mask deletion on MS-COCO validation dataset was used. So x-axis shows the size of instances in specific ranges, and y-axis shows the instance recall with the threshold 0.5. So the table summarizes the results. All of the methods improves instance recall at the cost of increasing FG ratio. So they actually in this paper chose the combination of these three models that maximize instant recall while keeping the FG ratio around 50% and use it for the E2E systems. Object detection. In order to compare detection results using various objectness masks, they use MobileNet as baseline OD model and pre-trained an ImageNet dataset. And used model for this proposal are in here, like vanilla, instant GT mask, box GT mask, SR mask, random mask, and OMG mask. So let's check the table. You can see this vanilla model has 36.47% zero values in the entire feature maps because of rectified linear unit activation, similar to reported to the other previous papers. So it issued 22.6 average precision. And instant GT mask 35.8 AP, which is 13.2 points higher than the vanilla model. It implies that background information is not necessarily essential, and high quality masks can help to achieve better accuracy for object detection. And in terms of computational cost, it requires only 33.5% of vanilla model. So the box mask, since the building and instance segmentation dataset is time-consuming and costly work, not all datasets have instance segmentation annotation. So you can see FG ratio. It is 13% higher than that of the instance GT mask model. And SR mask is spectral residual methods, is one of the saliency detection algorithm. It identifies specific areas of an image where unusual frequency information resides based on natural image statistics. So they didn't use the training data sets and run where, and it's run really fast. And when you check the FG ratio, you can see it is under 50%, the threshold 0.08. And it is the lowest AP among all the other models, even worse than the models trained with random masks. So it results from the fact that salient areas don't necessarily correspond to region where target objects exist. So in the case of Net V2, the input image resolution was used 256 square and for OMG and 512 by 512 for object detection network to reduce the computational cost for mask generation. And the generated mask is rescaled 515 by 515. 512 by 512 by bilinear up sampling before ArcMax output, and the computational cost was 9.2 for this model Net V2. So this figure shows comparison of instant recall of AMG masks generated from the standalone OMG model and the end-to-end model. And this model use the same training and inference schemes such as input size and data augmentation methods. And the masks the model exhibits higher instance recall than those generated by the pipeline model for all instance size. This experiment results shows the additional losses backpropagated from OD networks to OMG network contribute to the high quality mask generation. So in this table, it shows that the proposed, the used end-to-end model also achieved 1.2 points higher AP than the pipeline models as shown. It implies that improved mask generation by object detection losses also helps to enhance object detection performance. So the figure shows the average ratio of zero values at each feature map blocks for MS correlation set compared to the vanilla model. So you can see the vanilla model says 36.47% of feature maps are zero in the vanilla model. The proposed methods push this number 68.10%. This leads to reduction of computational cost. In this table, you can see the comparison of the proposed method to the other MAC reduction approaches using low resolution input, images, and small capacitor networks with multiplier option of MobileNet V2. As shown in the table, the model using the proposal method always outperform the vanilla models, even if some of them have larger MAC star than the proposal model. Yeah, this figure shows sample images with their feature maps and detection results for the vanilla model and proposed model. To visualize a feature map, average absolute feature values across channels at the end of bottleneck block averaged like 128 by 128 size. And the second row, the method generates a feature map where only a small portion is the foreground region. As you can see, this was the target one, and yeah, this is the generated feature map. As a result, MAC star value for each image is very small, as shown in the bottom area. This table 5 shows evaluation result of end-to-end model with heavy backbones. To evaluate the generality of the proposed method, the authors experimented with heavy backbone networks. This table shows MAC star reduction comparison to their vanilla models. So the proposed approach only used 64% and 69% of vanilla G MAC star. For VGG and RetinaNet models. And lastly, this table reports the evolution reports on MC COCO test. The result of 3 models is almost consistent with the experimental result on validation data. The evaluation results on this test can be seen in here. And it also shows the same trend, even if the data is changed. So as conclusion, they present a novel object detection framework. They propose an objective aware object detection method that processes only part of an input image where the objects are likely to exist, namely foreground regions. And this approach, they had a novel object detection framework that reduced computational cost and sparsifying activation, and end-to-end model architecture to incorporate the OMG network into a modern OD models. And experimental results also shows that the training with only foreground region is not harmful. And as a feature work, I mean, it can be like check, improve object detection accuracy. To evaluate the effect of state-of-the-art segmentation algorithm, so that they can improve object detection accuracy. Yeah. Yes, that was the end of the presentation. Any question?